Welcome back to our statistics learning session. Today, we'll be talking about asymmetry hypothesis as well as statistical tests. So, let's begin with a quick review of what we discussed in last lecture. We talked about null hypothesis and alternate hypothesis do not play a symmetric role. When we do some tests under null hypothesis, either we can not reject null hypothesis or we can reject null hypothesis, but we cannot prove that null hypothesis is true. Null hypothesis is good as only assumption that supports null hypothesis. We cannot prove null hypothesis. In this hypothesis business, we cannot prove anything. We can only reject hypothesis such that the alternate hypothesis is more favorable. It follows a trial logic where there is a person who has brought in front of a jury, and it is a job of the prosecutor to bring evidence to prove that this person is guilty. When jury decides that this person is not guilty, then it is not saying that this person is innocent, but it is saying that the prosecutor could not bring enough proof that this person is guilty. This is really a good example to follow when we are dealing with hypothesis testing. Now, let's move on to a test for hypothesis testing. This is called test statistics. It is a function that takes in your data and turns that into a output which can be either 0 or 1. This output 0 and 1 do not live in the parameter theta or estimate of our hypothesis. It does not live in the estimate of the distribution, but it lives in a separate plane where its value can be either 0 or 1. We can confidently say that this test statistics is a function called indicator because its output can be either 0 or 1. Does it make sense to you? It makes sense to me. Now let's move on to creating a test statistics for a case example. Here, the hypothesis testing H null hypothesis is P equal to half and alternate hypothesis P not equal to half. There is no issue in this example that either people have preferences on kissing left side or right side? Do they turn their head when they are kissing? Do they turn their head left side or right side? We assume with their preferences. It can be either possibility. But alternate possibility is that people tend to prefer left or right. That's the alternate hypothesis. If you look at this hypothesis, this hypothesis is called are disjoint, and they are complementary, meaning they are complementary, meaning they cover whole space between 0 and 1. If you look at the space here, let me go here. Let this be a line between 0 and 1 and half. This half is a singleton between 0 and 1, while and it is null hypothesis, while remaining space is H1. Therefore, it covers whole space between 0 and 1, and they are complementary and mutually exclusive. Let me go back to test statistics and talk a little bit more about the test function. Here we have test function called psi. When psi is 0, h is we cannot h is not rejected, and when psi is equal to 1, h is rejected. That means h not is rejected. That means we are looking h1 much more favorably at this point, because since h0 is rejected, the only alternative that is possible from our assumption is h0, which is some hypothesis, but that hypothesis is only good as its underlying assumption. We have to keep that in mind. Moving on to test function psi. Now question arises, how do we know that this psi function will produce 1? What time do we know that? Can you tell me? Well, we can go back to our previous exercises we did previously, and then we can take a look at this function we created, which is x bar n minus 5. That means it is saying that if x bar n is greater than half, then we can say that it should return positive, it should return 1. But do we need some margin of error in this? Yes, we do, because of some sampling variability, we can get slightly above half and slightly below low. We have to take into such variability into account in sampling when we are creating test statistics. Therefore, we'll have some buffer here. While we are doing this, we should also standardize x minus half into standard normal, such that we can use standard normal table to create such buffer. Therefore, we need to divide. For our example, we need to divide by 0.5 multiplied by 1 minus 0.5 divided by n and take a square root of whole of that and divide everything to x bar n minus 0.5. In this way, we have normalized our statistic test so that we can use standard normal table. Now question arises, this expression should be less or greater than some threshold. It should be greater because if the margin of if is more than some margin, then we can safely assume that we can reject the null hypothesis or null hypothesis is not true, and we can look favorably to our alternative hypothesis. Now question arises, since we already know what this expression should be, the only thing that remaining here is C. How do we decide C? That's a good question, and we'll follow up that in the next lecture. But main point here is that this expression we really calculated, didn't we? Yes, we did. We calculated this expression in our previous lecture, which came to be around 0.77. And one thing we are asking here is minus 0.77 is greater than this margin of error or margin of sampling variability we are talking about. Well, that's much for today. Let's quickly summarize what we discussed today. We discussed about asymmetry in hypothesis. We talked about test statistics, which is actually a function that produces two output, 0 or 1, based upon the data it feeds on. And to produce that 0 or 1, it needs some information called buffer margin or cutoff value or threshold. You can say anything. And for that, we need to calculate this value using standard normal table, which we'll discuss in later session. That's all for today. Thank you so much. I will see you next our next learning session. Thank you.